I completed the last experiment, and sir, it was very fine. The circuit was working very properly, and sir, now in next experiment, what we have to do, sir? You explain.
But the next experiment, Victoria, when will that be released?
It has been released already, Professor.
Yeah, it's been released, right? So that's an analog experiment, right? I don't know. Maybe it's characteristics of some diode or something. I don't know what it is.
Sir, yes, sir. It is like with the storm bridge.
Wheatstone bridge, is it?
Yes, sir.
Okay, yeah. So then that's okay. No, go ahead and do it. I think you will have the instructions are given, and there is some TA who will meet you next week to discuss that. If you have any questions on that.
Okay, sir. Thank you, sir.
So today, do you have any questions on the voltage transfer characteristic experiment? Yeah, Namai.
Yes, sir. Good evening, sir.
Good evening. Yeah.
So I had a couple of questions.
Yes.
Although we know that things differ in the real world, the practical is a bit different from theory, but I found this to be a bit weird that as expected, our VTC curve did not change at about 2.5 volts. Instead, I tried it two times and still mine changed at about 1.12 volts. So as the input went below 1.12 volts, then my output slowly started increasing, and only when the input went below 0.75 volts,
Yes.
it gained proper,
Correct.
high.
Ah. Okay. So there are two variants of this 7400. Okay. So there is something called 74LS00, 74HS00, or some variant like this. Okay. So this is done very deliberately in order to move the trip point of that inverter. Okay. So in this case, it is skewed towards the lower end, right? That means
Yes,
a small voltage is enough to trip it. Okay.
yeah, right.
So on the other hand, there are other things, inverters, where the trip point might be close to 2.4 volt or even sometimes 3 volts higher. So
Okay.
it is very likely that you will see variants like this. So
Ah,
you can just zoom into your IC, right, and find out the exact name and search for the data sheet of that name,
right.
right? Usually it will tell you what the trip point should be.
So I wasn't aware of the fact that in reality, in practical, there are different inverters also that exist that have different trip points. I thought it'll like if it's an inverter, naturally it would invert at about 2.5 give or take 0.5 volts for like error and all.
No, no,
So
no.
that's
That.
fascinating.
In fact, deliberately we don't tell you this because we want to make sure that you report the right measurement, right? You are not
Initially, I thought I took some wrong reading or my experiment kind of failed.
I know, but when
That's
you
why.
see it repeatedly, you must report exactly that, and then you must analyze why that is happening. Correct. Okay, so this is expected behavior.
Correct, sir. Understood. Thank
Yeah.
you.
Okay. Yes, admin. Why is admin raising hand?
Sorry, sir. Sir, what is the role of the capacitor? Why are we attaching the capacitor, sir?
No, first I have a question. Why are you admin?
Sir, I noticed now only, sir.
Okay.
My name is.
Okay. Okay. So the capacitor, right, or at the input, is it?
Yes, sir.
So see earlier we used to give something the voltage used to come from some other source which could be variable. So what the capacitor does is it will just hold that value for you. See, once the capacitor is charged, right, it will hold that charge for some time. So let's say that the input voltage you want to apply is 5 volt, but momentarily your voltage source that you are applying goes to 4.9 volt, right? Then what will happen? If the capacitor was not there, the voltage will be what?
4.9 volt.
Yeah, but now think about this case. Let's say the voltage dropped to 4.9 volt for just 100 nanoseconds. and then it went back to 5 volts. Okay. What will happen is this capacitor, because it has already been charged to 5 volts, it will hold that 5 volts for a very short period. So the capacitor will start discharging, right? Once the input goes to 4.9 volt, it will start discharging. Correct.
Okay.
But because the time constant of the capacitor is much larger than, let's say, 100 nanoseconds, it will appear to you as if the voltage is still being held at 5 volts. Okay, so this is called a decoupling capacitor that is used commonly in IC design, where you just use it to provide that additional current when there is a small droop in the voltage momentarily. It can't be used if you know that the voltage will drop significantly for long periods of time. It is only momentary drops that can be handled by these capacitors. Okay?
Okay, sir.
Yeah.
Can we add a noise and check, sir?
You can try. You can try.
How actually, how can we?
So what you can do is you can on that voltage, right? On that input, you can apply a sinusoid of, let's say, 4 volt with an amplitude of, let's say, 20 millivolt. DC should be 4 volts or something like 4 volts, and you apply a sinusoid of plus minus 10 millivolt amplitude. Okay.
Okay, sir.
Then it will, and then you put the capacitor and measure at the output of the capacitor, right? You will basically see it like this thing. But the time constant is important. See, that capacitor is just a low pass filter, right?
Okay, sir.
So what is happening? What do I mean by a momentary noise? Think about it. Okay. What is a momentary noise? The voltage is falling to, let's say, from 5 volt, it is falling to 4.9 volt for a very short period, let's say 10 nanoseconds, right?
Okay.
That means this is a very high frequency change, correct? In 10 nanoseconds, it's going to 4.9 volt and then coming back, correct?
Okay. Yeah.
So that means the capacitor, which is acting like a low pass filter, will cut out that, no?
Yeah.
That's all it is doing. That's what the job of the capacitor is. So actually, you have already seen this in your low pass filter.
Okay.
Okay.
Okay, sir.
Yeah.
Thank you, sir.
Yeah. Yes. Any other questions on the voltage transfer characteristics? See, the most important thing that you should appreciate, right, from this experiment is to see how much of noise immunity this inverter has or this NAND gate has, right? What will happen is you're going to have, like I mentioned in my digital systems course, right, in the first week, when I spoke about the voltage transfer characteristic and noise margin, you can see that the inverter can withstand a huge amount of noise. So even if there's like 10%, 20% of the supply voltage noise, right, this inverter will work correctly. That's why your digital computer today is a miracle, right? It has simply outperformed every other compute that has existed till today, simply because of this noise immunity. Under severe noisy conditions, this digital computer will work perfectly. Okay. Yeah, anything else?
Yes, sir. I have a question, sir. As
Yes,
per
please.
the weeks, sir, as per the week 6 content, you told about the tri-state inverter,
Yeah.
where we have a enable, sir, which controls the logic, input logics and the output logics. Sir, how is that enable is made, sir? If we have to do any other operations to make that enable, or sir, it is inbuilt feature
No, no,
in the modern.
enable is another input to that gate. Only when enable is one, it behaves like an inverter. Otherwise, it just floats that output.
Okay, sir.
Okay.
Sir, it can be VDD.
Sorry?
Sir, it can be VDD.
It can be, what do you mean by it can be VDD? The enable signal can either be VDD or it can be zero. If you want it to be VDD, I mean, if you want it to work like an inverter, it has to be VDD. Yeah. Any other question?
Good evening, sir. Can I
Yes.
ask?
Sumit, yeah, go ahead.
Yeah, sir. I have no doubt for this experiment, but I want a little doubt. Like for this experiment, we take only one NAND gate and draw the VTC graph. So
Correct.
my question is, can we do like cascading two NAND gate and then draw the VTC graph? Is there any additional precaution we have to take in mind?
Okay, so what will happen? Tell me. You tell me. If you take if you cascade two nine gates, what will happen? Tell me. Can you what will you expect to see? So you're saying you take NAND gate A, take the output of NAND gate A and connect it to input of NAND gate B and tie the other two inputs to VDD, correct?
Yeah, yeah.
Okay.
Yes, sir.
Now what do you think will happen? Tell me. So on NAND gate A's input, you are going to do this, potentiometer and change the input voltage from 0 to VDD, correct?
Yes, sir.
What will happen at the output of NAND gate B then?
Sir, I guess VTC looks similar, but little change, like
No,
slightly.
what to think about it? This question was asked in your assignment when we cascaded inverters.
Sir, I
Noise
think it will
margin
have
like
no effect, right? Because the inverted value will get inverted, so we'll get the same thing, isn't it?
Yes, sir,
No,
because
no,
of
but okay,
NAND
but
gates.
so I'll ask you this question. Okay, so you have NAND gate A followed by NAND gate B. You are giving the input voltage on NAND gate A. You are varying that from 0 to 5 volt, and you are plotting the output voltage on NAND gate B. What do you expect to see?
Sir, considering we hook up one of the inputs of both of the NAND gate A and B to high, then it
Yeah,
will simply both will act as an inverter. So the output of the first NAND gate will be basically the inverted version of our input, and the output of NAND gate B will be further the inverted version of the inverted version that we got.
but Namai, we are now talking analog voltages, right? What you're saying is true if I gave digital inputs.
Sir,
Okay, right.
I am
the
talking.
output will be similar to the input, right? If we are using two NAND gates, then there would be no effect of the NAND gate.
Okay, so what are you saying will be the output?
I think our output will either be 5 volts or it will be 0 volts, considering it's an ideal one.
Yeah.
No. Considering the practical one, what is considering ideal one?
As in, okay, if I so basically, my graph, it basically changed at about when it was less than 1.25 volts. So considering our input is anything greater than 1.25 volts, my output will be 0.1, it will not change. I mean, it will be 4.93.
Correct.
And vice versa for the other thing. So for example, my input my input, when it was less than 0.7 volts, 75 volts, it went to logic high.
Ah,
So if my input is anything less than 0.75, my output will be 0. It will be 0.16.
okay. Just wait 1 second. Okay.
Sir, could you please repeat the question once again, sir?
1 second. I'll try to sort this out. Wait, because this is an important question. But which just give me 1 minute, okay? Okay, wait. Just give me 1 more second. I'm just doing this. Uh, okay. Okay. So, yeah. Let me know if you're able to see my screen.
Yes, sir, it is visible.
Okay. So I have just plotted it as two inverters. Okay. Forget the NAND gate. Other two inputs are tied to VDD. So therefore, it's like an inverter. That's all. Okay. So now, what are we doing? We are going to change A to go from 0 to 5 volt. Correct? Is that right?
Yes, sir.
Assume that the V out versus Vn characteristic is the same for both inverters, that is shown here. Okay. So let us say A is some 1.1 volt. Okay. Tell me what will be the output voltage Y. How do you solve that correctly?
What's the 1.5 volt?
Let's say 1 volt or any voltage. What is the way to solve it?
Sir, I think first we'll convert this to a digital logic, either 0 or 1. Then
No.
we'll
Ramay, you cannot do digital logic 0 or 1 when we are talking analog voltages. I am asking you to plot. I am asking you to plot Y versus A.
okay.
A is going from 0 to 5 volt.
I will be also follows laser.
So Y will also be, are you saying it will be something like this? Something like this?
If there is any error, two NAND gates are same, that means they will equally follow.
Yeah, assume it's all same.
So it will exactly follow, sir. I think, sir.
Okay. How do you solve this
Exactly
problem?
follow.
Now, how do you solve this problem formally? Tell me.
In formal way, na normal way, na sir.
Here, whatever signal we are giving, sir, at the input of first inverter, sir, it is get inverted and the output is again inverted, sir.
See,
That's why.
again, this word inverted is a very digital term.
Okay,
There is no meaning for the digital term when we are talking analog voltages.
Please give some hints, sir.
Okay, so the way to solve this problem is A is the input for inverter 1, correct?
Yes,
So
sir.
based on the input A on this graph, you have to take, let's say that's 1 volt. Okay, let me show you that.
This graph
I'll-
is the first inverter or second inverter, sir?
Its graph is for both.
Huh?
Graph is for same for both inverters. Okay, let us say A equal to 1 volt. Okay, I'm just hypothetically saying this is 1 volt here. 1 volt. Okay, suppose A were 1 volt, right? So what you must do, you must on this curve for 1 volt, you must find out what V out is. Okay, what is that? That is very close to 5 volt, correct?
Yes, sir. Let's
Yes,
say
sir.
4.
Yeah, assuming that the maximum value, let me also mark that 5 volt. Okay, assuming that the maximum value is 5 volt, let us say hypothetically this was 4.9 volt. This value that I put, right, let's say was 4.9 volt. Okay, that means for an input of 1 volt to A, the value of X corresponding to that is 4.9 volt. Correct?
Yes, sir.
Now you take 4.9 volt as the input for the second inverter. Where is 4.9 volt on the input? That is somewhere here. You understand? Then you have to find out for that inverter what is this value. Correct?
Yes, sir.
You follow me? So now tell me what is the curve you will expect.
Sir, it will be the exact same, just mirrored over, like mirrored in the y with respect to the y-axis.
Shifted towards the left. Yes, sir.
No, think. What I am asking you is, what is going to be this transition region? Okay, you guys, now that you asked me this question, go back and try this experiment. You have 2 NAND gates, right?
Yes, sir.
Put them in series. Okay. Right?
Yes.
Put
Yes.
them in series and plot Y versus A, with A going from 0 to 5 volt. Tell me what curve you see.
Sir, here the Y graph was starting nearly from origin, sir. It will go right side. That means I think the slope will be increased here in case of Y.
Don't guess. Tell me exactly what will happen. Do you think the curve will be similar or what will happen? See, I told you the procedure to find it, right? I told you the procedure to find it.
So
How
the
to
graph
fit
would be,
formally.
so the graph would be just the opposite of it, of the result of the A part, the X part.
No, what do you mean by opposite? What are those? I don't understand what those terms mean. What do you mean by opposite?
That probably he means to say mirror symmetry with
Yeah.
respect to y-axis.
Yeah.
With respect to no, but that's not the point I'm trying to make. What I am asking you is, will the transfer characteristics have even such a slope between, let's say, Namai was saying, right? After 0.8 volt till something, there is an indeterminate region.
Yeah. So actually, with respect to this graph, it will be that. But when you consider like the graph that I got, for example, even if we do a mirror symmetry, right? I think it will be the same.
Okay. Now, okay.
No, sir. Please do.
You guys need to go back. Okay. Consider, see, I'm very surprised by this because this question is there in the assignment.
Yes, sir. Please.
I had given this question in the assignment where I cascade two inverters, and we highlighted one very important point of that here.
The Y graph will cut the A graph at some point, sir, at the middle, sir. Right, sir?
Okay, why don't each of you draw it on paper and take a photo and show me? I want you to draw the original transfer characteristic, and on the same graph, I want you to draw the Y versus A. Okay, can one of you, Namai, can you open assignment 1?
Sure, sir. Should I share my screen with the graph
Yes.
that I plotted?
Yes. Yeah. You plot it and show me that.
Yeah.
I'll stop sharing.
I hope it's visible.
Ah. Okay. Fine. But this is V out versus V in or Y versus A?
Sir, I considered V out to be pin 3 and V in to be pin 2. And I explained that in my video. So I think it wasn't
No,
corresponding.
but this is just this is the output of one NAND gate, no?
Correct. Yeah.
I am asking you, how will the VTC, if the same experiment, if I do with two NAND gates, how will it look?
Yes, sir. I'm just drawing that. I'll just take a second.
Okay, cool. Fine, do that. Yes, Hemant. Yeah,
Yes, sir. Sir, I have drawn on my paper, sir. Can I show this, sir?
yeah, show the photo. Yeah, you can share. Yeah. Yeah, Namai, can you stop sharing?
Yes, sir.
Hey, Hemant, please share
Yes,
the
sir.
photo onto your computer and share that screen. Don't show it to me on the camera.
Okay.
Yeah. Can one of you also share the assignment 1? Share your screen, open assignment 1 and share it.
Sir, I have tried drawing the graph. So
Ah,
can I share it?
yeah, 1 second. Someone showed me this. Show me this practice assignment. Consider with both inverters having VTC as shown below. Okay. So how did you solve this problem? Tell me. Just go up a little bit. Show me the picture.
So taking the slope of it.
No, slope is fine. That's okay. But you had to do exactly what I told you, right? For this input voltage, find the output voltage. Treat that as input to the next inverter and find the output voltage.
Yeah, sir.
So what happened? So for 0.38 volt, what is the answer? Here, in this case, tell me. For 0.38 volt, the answer, okay, just look at that curve. Look at that curve. For 0.38 volt, right? For an input of 0.38 volt, you agree that the output will be of the first inverter will be near 0.8 volt.
So since it is high, the output should be low, right?
No, what is high, low? I don't want to hear words like high and low. That's a meaningless thing to say when we are talking of analog voltages. I am trying to tell you to plot the voltage transfer characteristics. You sweep the input voltage from 0 to 5 volt. Tell me what the output voltage is. So if the input is 0.38 volt, you agree that the output will be somewhere close to 0.8 volt of the first inverter.
So around 0.7.
Around 0.7, it doesn't matter. 0.7,
Yeah.
right?
Yeah.
Now, if to the second inverter, if 0.7 is the input, what will be the output?
0.
Exactly. So what you saw as a, the indeterminate region in the first inverter, right?
Yeah, sir.
Actually is not an indeterminate region when I put two inverters together. Because 0.38 volt is resulting in an output voltage which is perfectly zero. You get my point?
Yes, sir.
So if I plot this together, right, that indeterminate region will shrink.
That is what it is happening over here also then.
Exactly. That's what is happening. That is the beauty. That's what I'm trying to tell you. That is the beauty of this inverter, of this CMOS inverter or TTL inverter. It is so resilient to noise. So even if the first inverter sees some noise, it gets nullified by the second inverter. And the voltage gets restored back to logic levels correctly. So what was a noisy 0, 1 at the first input of the first inverter becomes a noise-free 0, 1 at the output of the second inverter. You understand?
Yes, sir.
That this is the key part. I'm telling you, I'm going to ask a question on this in the final exam. 100% I'll ask. Okay.
Yes, sir. I had drawn this graph somewhat like this only, sir.
Yeah. Okay. So I would like you to now do this experiment and see for yourself when you cascade two NAND gates. What is it that is happening?
Yes, sir.
Okay.
Yeah. Sir, I had a request from Victoria ma'am that I might have received less components because as everybody is saying that they have received two NAND gates, I have received only one. So can Victoria
No.
ma'am?
What is two NAND gates?
I
You
mean,
get only 17400.
so as you said that we have to perform using putting them in series.
Hey man, don't tell me you have not even seen how many gates there are in each IC. How many NAND gates are there in one IC?
Sir.
Huh?
Four.
Four, exactly. So why do you need two chips for that?
Oh, I thought students have received more
No,
components.
no. They have not received nothing. You have to do it with the same IC. Just consider one more NAND gate. That's all.
Okay.
Okay. Yeah.
Could you please explain once again, sir, this concept, sir? Once again, noise free.
No, did you do this assignment?
No, previous term I have did, sir.
No. So what? Say this question is there previous time also.
Yes, sir.
So okay, now you do this. You do this question here now. If the input is 0.38 volt, what is V out? So can you, whoever is sharing this, can you go up and show that figure? There is a figure associated with this, no? Down. Yeah. Up. The two inverters. Slightly up.
Maybe the third question, I guess. Third or fourth.
Yeah. This is the picture, right? Same thing. V in, V out 1, V out. V out 1 is that intermediate node. Okay. Right? So now go down to the transfer characteristic. So see this. Now go V out is here. I am telling you that the input voltage is 0.38 volt. What is V out 1? What is the output of the first inverter? How do you do this? So how do you do this? Hello? Can you hear me?
Yes, sir.
So how do you do this? When the input is 0.38 volt, what is V out? What is V out 1?
Sir, we calculate the slope by the formula y2 minus phi1 upon x2 minus x1 equals to,
Correct? Yeah.
and then we get the slope, and then we use y equals mx plus c to determine the y coordinate.
Correct. So what is the answer? Someone calculated and told me, no?
0.67, sir.
0.67 volt. Correct. So how do you find the output of the next inverter then?
So then after that, sir, we treat that as the input for the next inverter, and we
Correct. So that is 0.67 on the x-axis. Correct.
correct. 0.67
therefore-
would simply result in 0.
Exactly. So what resulted in a value that was not either 0 or 5 volt, 0.9 volt is now resulting in exactly 0 volt, right?
Correct.
So therefore, what will happen? That indeterminate region will simply shrink.
Right.
Okay. So it is not going to be a mirror image alone. It will go 0, 0, 0, but there'll be a very small region where it will be indeterminate, and then it will just simply, like, it will shoot up and then go back to 1. You understand?
Yes, sir.
Okay. So the other way to look at this, right, is, see, the gain in that region is actually the slope, right? You agree? If you remember my digital systems lecture, first lecture, I showed you how to do that small signal analysis, right? Using the gain.
Yes, sir.
Correct. So what is the gain of this guy? Tell me. In the indeterminate region, what is the gain? It's just a slope. It is just a slope, right?
Sir, 1.0975.
No, how can it be 1.0? Because
Minus.
it is, no, it is 0.9 divided by 0.12, correct? Minus of 0.9 by 0.12, correct?
Oh, yeah, sorry.
Huh?
Yeah.
How much is that?
So minus 7.5, sir.
So
Right, minus 0.9.
0.9 divided by 0.12. Okay. Minus 7.5, correct?
Yes.
Minus 7.5. Now, when I cascade two amplifiers, what will happen? The gain will multiply, right?
Yeah.
That means what is 7.5 will become 7.5 square, correct?
Yeah.
That means the gain will become approximately minus 49 or plus 49.
Correct.
So, see, the gain determines the indeterminate region, right? See, if the slope of this line was lesser, was not as high as, the modulus of the slope was not as high as 7.5, you would have a larger indeterminate region, correct?
As the gain increases, the difference between the x coordinates would decrease, and hence
Correct.
indeterminate period would also decrease.
Correct, right? So now when I cascade two NAND gates, the gain is actually going up as gain square. Right? So actually, if you look at the combination of the two NAND gates, they are like a single gate with a slope of 49. So that means the indeterminate region has to come down. Okay. So what I will do is, okay, good. Now that I know you guys have trouble following this, I will make a separate video explaining this out clearly. Okay.
Yes, sir.
Okay.
Yeah.
Good. I think this was a good class. Go back and think about what I said. Okay.
Sure, sir.
But that's the reason I gave this question. And I'm telling you, you will get this question in the final exam. I'm telling you right now. Okay.
Yes, sir.
Okay. Right. Okay. You will get a variant of this question, I'm telling you. That will test this idea.
Thank you for the insight, sir.
Yeah. Okay. But I'll make a separate video for this and I'll upload. Okay.
Yes, sir.
Yeah. Okay. Chalo. Then thank you all. But please try this experiment and see for yourself.
Yes, sir. Sure.
Okay. Thank you guys.
Thank
Bye.
you, sir.
See you next week. I think next week is analog. I'll see you the week after that.
Yeah, okay, sir.
Thank you. Bye.
Yeah.
Thank you, sir.